So yes, I promised to discuss momentum, supercurrent, and heat flow in ballistic graphene. But then yesterday, I actually listened to some of the talks, and I figured out that 3 or 4 words out of 10 I don't understand. So what I suggest, which was supported by Ella, is that we kind of, I'll give a very wide review, and we'll try. I mean, I have 40 slides. We don't need to go all the way to 40. We can go to 10, but the point is hopefully we'll get something out of it. The simple, more simple than the title is just what we are interested in actually studying dynamics of electrons in crystals. So any questions? No, so basically this slide is here to kind of really promote discussion. So if you don't understand anything, just ask. Don't wait to the end. There will be nothing at the end. So what we would like to do is actually look into kind of simple structures and really exploit physics on a wide range. And I like this kind of illustration. What you see here is a kind of a crystal of graphene. We'll discuss what it is. And there is a kind of a light source at the back, and it's pointing into space or something like that. So in principle, what we try to do is we try to make simple structures. We try to make crystals in which we change the symmetry of space and really look into new physics or new kind of particles and really study the fundamental physics out of it. Now, everything is quantum mechanics, actually, which is pretty boring, but there is still a lot to study. Okay, so why? So first of all, the experiments that we do involve electronic transport, which means it's a very simple experiment. We take this crystal, we connect contacts to it, we drive current, and we measure voltage. Okay, or we do the other way. I don't know, we put voltage, we measure current. This is basically all we do, and we try to figure out what happens. And the reason we do it is what we tell ourselves is that it's very interesting. Okay. And as I said previously, the crystal kind of puts us in a new playground. So we can really change, we can do many physics which is not there if you do it in vacuum. For example, if you do it in CERN, look for fundamental particles. Actually, in crystals, we can invent many particles, new particles, and study the physics of them. So maybe very main examples from the last century is superconductivity. Who doesn't know what is superconductivity? Okay. Maybe I'll say it so everybody knows. Okay, so I can run to the 40 slides. So superconductivity is a state where there is no dissipation. So if we do the experiments that I discussed previously, we put current and we measure voltage. This is what this guy did 100 years ago. He did that. This is the voltage. And this is temperature. So he was just doing this experiment and changing temperature. He go down below very low temperature. And what happened is that this voltage dropped to 0. If we divide the voltage by the current, we call it resistance, and drop to 0. Now, this is very weird because usually it corresponds to dissipation. If you have a process, you know, you're trying to run some energy, some of the energy get lost. And here it dropped to 0. So he was, he did it, I mean, he could see that it's really 0. Now today we can actually see that it's really, really 0. It means that if you take a kind of a coil of this material that he was using and you drive electrons in it, you come back after the age of the universe and nothing happens. I mean, you don't need to put any gas, they will still go running, nothing changes. This is really, really zero energy and zero dissipation. And it's kind of a pronounced effect where you have a phase transition. It means that the electron actually order in a completely new way that allows you for new things. So you just change here the temperature by 1 degree, and they go from highly dissipating to no dissipation whatsoever. Another very cool effect is a quantum Hall effect. Anybody who doesn't know what is quantum Hall effect? Okay, that's cool, that makes sense. So this is also a quantum mechanical effect. In quantum Hall effect, the resistance doesn't drop to zero. It becomes a constant value. Now this is kind of weird because if you take, a wire and you drive current and you measure voltage, if you will make the wire twice as long, usually the voltage will go up. This is called Ohm's law. Okay, or if you kind of, drill holes into this wire, the resistance will change, yes? Now in this case, it doesn't. You can take the system, you put it in this phase, which we call quantum Hall effect. It doesn't matter what you do to the geometry of the sample. It doesn't matter actually which crystal you use. You can use graphene, you can use gallium arsenide, you can use silicon. You get exactly the same number. And when I say exactly the same number, it's by 12 digits, exactly the same. Okay, so today we are actually kind of determining what is the volt by using this kind of measurements. So this is really cool. You take a device, you don't care what it's made of, what you did to it, you put current, and you will see a voltage which is exact by 12 digits. Both of these effects were obviously got the Nobel Prizes. And okay, so people found out, I told you it's quantum mechanics. We know, we just write a Schrödinger equation. In principle, we know the physics. But luckily for us, it's not, because most times we can't really solve Schrödinger equation. So this is why we actually need to do experiments. So if you take more than a bunch of particles or degree of freedom, you can't really solve the equation. So you really need to do an experiment in order to see what happens. So this is why we have jobs. Again, very good examples for that is high TC superconductivity. So I explained what is superconductivity, and people kind of figured out why it happens like 50 years ago. And when they figure out, they said, okay, there's a limit to the maximum temperature that it can happen. And what happened next? We got high TC superconductivity, which means these guys actually show that this limit doesn't work, and we can get new type of superconductivity. Okay, so this is why experiments are important. And for this guy, there is another effect that was actually found experimentally. Very surprisingly, it's called the fractional quantum Hall effect. So in this case, we kind of understand exactly what happens, and it has to do with the fact that the charge comes in quanta, and here we can fractionalize this quanta. So in principle, the takeaway message is that it's very interesting to play with these crystals, and you can find new things which are unexpected, or actually test things that you do expect to happen, and you can get the Nobel Prize for that. Okay, there are other applications. So field effect transistors also has to do with this crystals like silicon, and not with Steve Jobs, like other people think. Superconductivity, we get MRIs, and today we have a kind of a new era, or a lot of funding going into this quantum world, where we're trying to figure out how to really control the quantum system, to make sensors or maybe computers that can solve for us this Schrödinger equation. Okay, so what is graphene first? I'm going to do that with graphene, or many people do that with graphene. So graphene is just, you take graphite, which is just carbon in hexagon, and you separate it into layers. And that was done by these two guys in Manchester. And actually, it only takes a Scotch tape. So you remember this high TC I discussed previously. Lots of money went to kind of figure out what happens at high TC. And now we actually got kind of have a new insight into that by doing this kind of crystals, and it only takes Scotch tape to do that. So, so for Yael, I usually say that equipment is very, very important. We must get the best equipment to get some progress, but in principle, in my view, one of the biggest discoveries in the last 30 years was done with the Scotch tape. So the students should not complain about equipment. Okay, and today we have many materials which are like graphene. They are only one layer of atoms, and they have different properties, and we can actually combine them to create new types of crystals. So not only this gray pencil, we have many colors. And the field today is called van der Waals heterostructures. So in the plane, this material has this covalent, very strong bonding. But in between the planes, there is this van der Waals force, and you can actually take them apart and put them back together and make whatever structure you want. And they have a different, each of these compounds can have a very different properties. It can be a metal, an insulator, a semi-metal, a magnetic material, and so on. Okay, so why do we work in particular on graphene, and why not? So these are the superlatives of graphene. If you take this single atomic layer of carbon, it's actually the strongest material we know. It's definitely the thinnest. It's strong in the sense that it's very stiff. It means the Young modulus is huge. If you try to stretch it, you need the highest force. But if you do apply the high force, it will be actually the most stretchable. So you can actually deform the unit cell in this hexagon by 20%, and the material still holds. This is much, much more than any silicon or 3D crystal. It's a very good conductor of heat, of electrons. It has something which is called mobility, which is very high. I will discuss what it is. And it's very impermeable. So if this only one layer of atom is actually impermeable to any atoms, including helium. Nothing can go through. So there's many applications, actually interesting physics involved in that. Okay, so one last thing about these layered materials, we have a lot of control with them. It's not only the material on their own, which are very interesting, that we can actually control the system to create many, many interesting new crystals, a new system. And the reason is that, first of all, everything is surface. All the material is just surface, so you can directly kind of approach all the atoms. You can add the layers. And on these scales, the scales of the atoms, so this is like below nano. On the scale of the atom, we have this tunneling that actually this is what controls the properties of the material. And if you have control on this scale, you can actually really change the inherent properties of this material and really change the symmetry. So for example, many of these materials, they are kind of, have something that we call the broken inversion symmetry. So the atoms are different and they don't have an inversion symmetry. That opens up gaps, for example. So if you take one layer, it doesn't preserve inversion symmetry. But if you take two layers, it does. So if you go from a single layer to a bilayer, the properties completely change. And the last control is that previously people used to make, heterostructures by growing materials one on top of the other. So you put a lattice, then something grow on this lattice and another thing on this lattice. Here we kind of take the two lattices and we place them together and we can actually control the twist angle. So this is a new degree of freedom, and we can actually create this kind of moirés, and we go to this super lattice structure where the wave function is still coherent in a sense, and we can actually also change the inherent properties of tunneling by controlling this twist angle. Okay, so we are interested in this new physics or new particles. We call them quasi-particles. They are excitation of the crystal. And we can, in these materials, we can actually control the dispersion. This is the fundamental properties of these particles. So if you have, a free particle, you have a parabola. The energy versus, this is the energy versus the momentum. So usually you have energy equals momentum squared divided by mass. Okay, that's what happens when you throw a stone. And this is what happens in most materials, metals or semiconductors like silicon. Now, in these materials, in graphene, for example, because of the symmetry of the lattice, you get something completely different. The energy goes linearly with momentum, and this is something similar to light. Okay, it means that the velocity of this of these waves is fixed, doesn't depend on momentum, and you can get kind of relativistic effect. Now this is not light, this is electrons, this is fermions, so in a sense it was really new and really cool. And again, so if you take 2 layers of graphene, this kind of, you change the symmetry, you go back to have this parabol, and what is cool about this thing is that you can actually apply an in-plane field, electric field, and you can change the inversion symmetry, and you can open up gaps between these 2 parabolas, which is something that you cannot do in a material. You have silicon, this is the band structure you have. Here you can kind of get a gate to tune not the density, not how you occupy the state, but really how you change the dispersion itself. And there are also properties that has to do with the symmetry of the lattice. We call them pseudospin. It's similar to the regular spin, but it's kind of an internal degree of freedom. And here, for example, what you see here with the twist angle, you can actually, by changing the twist angle, you can continuously deform this dispersion. So here again, this is energy and this is momentum, and you can get crazy dispersions. And here actually, people recently found a superconductivity. Okay, questions?
Question?
Yes.
The previous slide, the first case is the ultra-relativistic expansion, right?
This one.
No, the previous one.
This one.
Yeah, it also has a regular term, but you neglect it.
No, if you this one.
Yeah, no, this one, the third one. The massless fermion.
Graphene.
Yeah.
Yes.
So it's approximation.
Well, everything is approximation, but this is a very, very good approximation. The velocity here is linear to a very, very good extension.
Just the momentum is high.
So actually what happens here is, it's not because the momentum, even here, yeah, obviously if you go to very low momentums, yes, it will degrade, but let's discuss it in more details. But in principle, no, you don't need to make a lot of assumptions to get that. And this is indeed what happens. It comes from the symmetry. Basically, you preserve both inversion symmetry and time reversal, and that actually protects crossing, which means a linear dispersion. Okay, so this is the cousin of graphene. It's called hexagonal boron nitride. I call it the best insulator, actually. So this is the BN. And it's very similar to graphene, and it has 2 atoms. So it has nitrogen and boron, not only carbon, and due to that, you actually break this inversion symmetry and you open up a gap, and it's a really, really good insulator, and it's insulating from a single layer. So what you see here is really the current versus voltage, and you see that you have something non-linear already for 1 layer. And 2 layers, 3 layers, so on, you can actually control the tunneling barrier by 1 atom. A very good barrier. And what we do, because it's a very good insulator and we have this graphene, which is a very good conductor, most of the devices that I will show you is just taking graphene, put it in between the boron nitride, and this way we protect it, and we can study the dynamics of electrons in it. Okay, so now why to study ballistic systems? So ballistic is kind of the easiest, the most simple case, because once you have a ballistic system, then you can throw things in. You can throw defects in, which usually we don't have ballistic system. We always have defects. So if you can get a ballistic system, you can always throw in the defects. You can really study how electrons transfer their energy to the phonons, which is what we call heat transport. You can hopefully study collisions of electrons. So when we study dynamics of electrons in crystals, actually we say we only have 1 electron, because the probability of an electron to be scattered by another electron has to do with the Fermi statistics, is very, very low in these materials, in most materials. So, and actually I will show you today a case where it doesn't happen. And we can really look at electron-electron collisions. And we can actually turn this ballistic system to a superconducting ballistic system, which is also part of the research that I will show you. And it's hard, okay, because it's not vacuum. So when you discuss ballistic electrons in crystals, it's not like you have a vacuum tube and you drive charged particles in between, because it's really, these electrons sit at very high energies. the density of electrons in a crystal is huge, and then you need to really occupy many momentum state that takes you this electron to a huge energies. So the electron in crystal moves relatively close to the speed of light anyway, unlike in vacuum tubes. Okay, graphene versus other ballistic. Okay, so when we're discussing ballistics in graphene, first of all, it's know where to come from. So the best ballistic material previously is called gallium arsenide, similar to silicon. And to get these systems, you need to have this very expensive molecular beam epitaxy system, which can actually take atom by atom and let them kind of grow on the surface. But people have been able to do that for many years, and they got this huge mobility. Here the axis is mobility, is kind of what is the mean drift velocity of these electrons. If you apply electric field, then all electron will drift somehow, and if the material is very clean, we call it high mobility, and they will drift efficiently. And when the system is not very clean, then the mobility will drop. And this is different years. You can see that now mobility goes to 20 millions or 30 millions in gallium arsenide at very low temperatures. Okay, in silicon at room temperature, mobility is something like 100. Okay, this is tens of millions. In graphene, we don't use this fancy ultra low vacuum system. We just use Scotch tape, a very simple microscope. We protect it, and we get very high mobilities. They sit here on the range of 1 million. Okay, so we're not really here, but still, taking into account that this is done in ambient conditions, it's amazing, yes? Because in principle, you would expect molecules or other particles to sit on your surface and really create electron scattering. Okay, so how come it does go to millions? And actually, I will show you that it can go more than that, and we kind of figure out what are the main reasons for scattering these days. And the reason that it happens, this amazing thing, is that these materials are very inert. Okay, so the way that we make them, by the way, we put this singular, we do the Scotch tape, we put it on a polymer, and then we kind of stamp the polymer on a surface and stamp the materials one on top of the other. Okay, really stamp. We work at the post office, basically. We're stamping things. And the cool part, because these materials are there are no free bonds at the surface, so really when molecules go to the surface, they don't really tight. They don't really bind heavily. So if you come and you actually push them with this van der Waals force, like you do when you change the screen of your phone, and you try to avoid these bubbles. So we do the same thing for molecules at the surface. And actually, we can get to perfect surfaces. I will show you, there are surfaces that we have no defects. 5 minutes, okay. So it happens for part of these materials, and this is why it's so good. You remember, so if we do it with graphene, what we notice is that actually the mobility at room temperature is much better than all the previous crystals. So there are better ballistic systems than graphene at low temperatures, but at room temperature, no way. It goes order of magnitude better than the best ones. And this has to do with the stiffness and actually the dispersion relations. So this is interesting, and we can use that to get new physics. We can have high mobility at high temperatures. And we did that to see how electrons scatter off each other. So usually when you heat up the temperature, the reason that the mobility there drops in boron nitride, in gallium arsenide, is that you add phonons, and they scatter the electrons. In graphene, it happens much less. So you can really get to a case where the electron scattering become dominant. And temperature is very important because of this Dirac statistics. So in order for electrons to scatter from other electrons, you actually need to have free momentum configuration, so you can, or momentum states that you can scatter off, and this was kind of cool. So there are many theories, and actually we were able to do kind of a simple experiment and look at kind of a negative resistance that appears due to a formation of vortices due to this electron, so when you can discuss collisions between the particles in your system, you go to a kind of a hydrodynamic regime, and you can see some kind of a non-uniform flow of particles. And by analyzing that, we can actually measure this distance between electron collisions, and we could see that it's pretty close to theory. And actually, the theory we can learn from for some kind of a scattering mechanism by having this data, and it's a big thing now. So many people are looking into that. Okay, so ballistic devices, we take the same devices, now we put them in a field effect device, and we want to study the ballistic flow of electron in a field effect device. And since I have 5 minutes or 2 minutes, I used to have. Okay, so what we also found about graphene, which is very good, you can actually contact graphene very well. So part of this unique properties, as we said, is that the in-plane bonds are very, very stiff and are saturated because of the other carbon atoms, but the out-of-plane bonds are quite inert. And if you want to really create a good contact to graphene, you need to use the edges. There was a poster done in Bal yesterday discussing how the edges are the only important things in transport of graphene, and we know that for many years. And we can actually use that to improve it and to get very good contact resistances. So if we discuss field effect transistors, so in principle, this is where all the materials in the world exist, and graphene actually goes to here. So in this plot, you can measure what is the contact resistance and what is the channel resistivity, and you want to have a very low contact resistance, very high channel resistivity to have a very efficient or a field effect transistor that can work at high frequencies, and actually graphene today is by far the best. Okay, that's it. Questions? Now maybe I'll go to the end. So momentum, I said I will discuss momentum, heat.
Oh, you were great.
Optimistic.
No, I said 10 slides.
I have questions.
So momentum, supercurrent, and heat. So we found out how momentum is being transferred by the collision between the particles themselves. And at room temperature, it's like 100 nanometers, which is an important insight. The supercurrent, so actually you can make field effect devices with graphene where the supercurrent is limited by the dimensions of the junction in a ballistic way, which means that the Cooper pairs also doesn't, or the time that the Cooper pair takes to cross from one side to the other is as if they are doing a ballistic movement and not a dissipative movement. And heat, the way that electrons transfer their heat to phonons in graphene is also very, very unique and has to do with very particular type of defects where you take out only one atom. Okay? That was the conclusions. Yes.
Questions, Gael?
Okay, so the discovery of the fractional quantum Hall effect was entirely unexpected and
Yes.
generated entirely new physics. The quantum Hall effect, in some sense, it was the same story. Here, the big story behind the graphene was really the material aspect, the fact that you can actually, that graphene is actually a stable thing. That was the big debate. The physics was pretty much well known, so when people started doing physics with graphene, it was basically, I mean, the theory that you showed was already there, and it was just basically, demonstrating
what type
it.
of, yes, but
So-
for example, doing
No. So
Okay.
the question, this is what I want you to
Okay.
explain. What is the new physics frontiers that are
Okay, so I was trying to explain that with this cool view of the different band structures. So indeed, the band structure of graphene was calculated in the 50s. That is correct. And when it was clear that when you will have that, when you can isolate graphene, you will have that. But once you have this band structure or this dispersion, you can do many sets of experiments to test how does these particles behave. So Klein tunneling, for example, and how Dirac fermions behave under magnetic fields, and things like that. These are things that were explored ever since it was discovered, which is new and was not expected in this sense. Okay, this is kind of a new physics that happens over the last 10, 15 years. What is new today, which is what you're asking, what if we look to the future? So this is, what I showed here is very new. Playing with the electron-electron scattering is very new. It was impossible in the past. Usually, if you have a crystal, you will have phonons that will kill you or will cause the electron to scatter way before that. But in my view, it's a small thing. Really, today, graphene evolved into these many layered materials, okay? And so the first question is, graphene proved that it's possible to isolate single layers of materials, and now we have many of these materials, and we can control them in a very profound way, which we cannot do in three-dimensional crystals. Okay, so this is one very big thing. We call this van der Waals structures. Or also the materials on themselves. In the last 2 years, we had new ferromagnetic materials. That happens. Ferromagnetism is another thing. So in principle, graphene or lattice should not be stable over an infinite scale at 2D. But graphene is stable, and people knew that if you have a finite space, it will happen. And now we have many of these materials, and it's finite for us. The size of the flake is finite, but for the physics that we're studying, it's infinite. So in a sense, it gives us whatever we need. It's really a dream for a material science physicist. It's a dream. And the other concepts which are kind of new these days is this twist angle, the ability to create really super lattices, which are kind of perfect. So there is a scale, the nanoscale, the 10 nanometer scale is a very, very interesting scale of lattices. Because, for example, you can push a flux quanta into this scale by a magnetic field that we can apply on Earth. We didn't have really crystals with dimensions of 10 nanometers in the past. We had them, they were not perfect. They would not really give us a dispersion, which is something that happens in a crystal. So crystal is very good. Once you have a unit cell, it will be the same unit cell all the time. If you try to do that on a 10 nanometer scale, it's very hard. So this twist angle actually does it much, much better than any previous system. And in this sense, these super lattices on the 10 nanometer scale is very unique. What? This is one of the, yes, so it's superconductor, it does a multi-insulating state, it does a lot of physics which we could not understand previously and could not control. Now we can actually control that.
That's possibly the historical point that, von Klitzing was using,
new materials give you new physics.
Well,
yes.
It wasn't really new, but it was really
yeah, but he was kind of pushing the limit.
And
today there are many, now it's actually, we have too many options. It's very hard to choose which one to focus on.
And Sui and Stormer were also using the state-of-the-art material that nobody had. That it's not just the material; it's also the device.
It was usually in physics we have some predictions, and we also know that if we go to a new place, we can find probably new physics. And so with this direction, I think goes in two ways. The twist angle, for example, superconductivity was also predicted, but to tell you how many people believe that it will actually, so it was predicted that it will be interesting. The flat bands were predicted, but to see superconductivity, that was, nobody would know what would be the ground state. And now we know that it can be either that or that.
There's one comment about the 10 nanometer scale. You speak about atomic crystals that make of carbon atoms.
No, in the twisted case, we have a super lattice which is caused by the moire. Or periodicity, it's not really.
Also, refer to molecular crystals, so you can get to the molecular crystals made of organic molecules.
But then the periodicity will not be perfect enough that you can, it will be a very different case.
It depends on the quality of the
Okay, let's discuss that later because we are behind time and schedule. Thank you very much for the heroic effort to be clear.